Each year, over 1 billion people across India look to the sky, waiting for the monsoon, a force that shapes their lives, culture, and economy. The monsoon is more than just rain, it's the heartbeat of a nation, celebrated in poetry and song, and vital for farmers whose fortunes rise and fall with its arrival. Yet this life-giving deluge is unpredictable, sometimes bringing bounty, other times disaster. Despite our satellites and supercomputers, the monsoon remains a mystery, defying precise prediction. Why does it flood one region and leave another in drought? This is the billion-soul question. Our understanding is incomplete. The monsoon is a complex, chaotic system that challenges even the best scientific minds. Each year, its arrival is both a promise and a gamble, a puzzle that holds the fate of millions. The quest to understand the monsoon is one of science's greatest challenges, with answers scattered across continents and oceans. The Indian monsoon is a story of extremes. Floods in one city, drought in another. Mumbai's streets can vanish underwater, while nearby fields crack under relentless sun. The same system that brings life can also bring destruction or devastating absence. This paradox, too much rain or too little, defines the monsoon's mystery. It's not a simple on-off switch, but a sprawling, unpredictable organism shaped by countless factors. Predicting its behavior is a matter of survival, not just science. For governments and over 1 billion people, the monsoon's rhythm determines prosperity or hardship. To understand it is to grasp the very pulse of India. Join us as we journey from Kerala's classrooms to high-tech labs, chasing the secrets of the monsoon. The monsoon is powered by the sun, the ocean, and the turning earth, a planetary drama. It's not one storm, but two branches racing and colliding in a complex aerial ballet. Despite modern technology, forecasting failures are common. Hidden variables can tip the balance. Jet streams, Himalayan snow, ocean currents, even distant dust storms, all play a role. Our tools have evolved, but each answer reveals new complexity. This is more than weather. It's humanity's struggle to predict and adapt to nature's chaos. The monsoon's secrets are waiting to be uncovered. The monsoon isn't just rain, it's a planetary heat engine. As India heats up under the summer sun, warm air rises, creating a giant low-pressure zone. This vacuum pulls in cool, moist air from the Indian Ocean, setting the monsoon in motion. The reversal of winds, from dry northeast to wet southwest, is the true monsoon. It's a breathtaking display of thermodynamics powered by the sun and shaped by geography. In classrooms, children learn it rains not just because it's the season, but because the planet is breathing. The monsoon is an ancient, powerful dance between land, sea, and sun. This cycle is a climate engine dictating life's rhythm across the subcontinent. The monsoon is no single wave. It's a two-armed giant. The Arabian Sea branch slams into the Western Ghats, unleashing torrents over Kerala and Mumbai. The Bay of Bengal branch sweeps north, drenching the northeast and curving west along the Gangetic Plains. These two arms interact, compete, and converge, creating regional variations and unpredictability. The fate of the season hinges on their delicate dance. A misstep can mean drought or flood. Predicting the monsoon means understanding two intertwined, semi-independent systems. It's a meteorological ballet, with consequences for millions. The monsoon's complexity is what makes it both vital and mysterious. This two-armed monsoon is, at its core, nature's most magnificent delivery system. It is a continental-scale irrigation project designed by physics and geography to transport trillions of tons of water from the ocean to the arid interiors of a vast landmass. This is not just a random scattering of rain, it is a structured, sequential process. The arrival of the Arabian Sea branch on the Kerala coast is just the opening act. From there, the monsoon embarks on a slow, methodical march across the subcontinent, a journey that takes more than 6 weeks to complete. It advances day by day, a creeping curtain of cloud and rain that gradually covers state after state, bringing relief and life wherever it goes. The progress is tracked with feverish anticipation by meteorologists, farmers, and policymakers alike. The Indian Meteorological Department, or IMD, publishes daily maps showing the northern limit of monsoon, a line that inches its way across the map of India like an advancing army. This line represents the frontier of hope. Its steady progress signals a normal season, while any prolonged stagnation is a cause for national anxiety. The system is designed to deliver water where it is needed most, first to the coastal regions and then pushing deep inland to the agricultural heartlands of the Gangetic Plains in central India, which are far removed from the oceanic source of moisture. The success of this delivery is paramount. However, this delivery system is also incredibly volatile and prone to disruptions. The journey of the monsoon is not a smooth one. It proceeds in fits and starts, characterized by periods of intense, active rainfall, followed by break periods where the rains weaken or cease for days, even weeks. These breaks are dangerous. A prolonged break during a critical crop growing phase can be just as damaging as a full-blown drought. What causes these breaks? The answer lies in the chaotic interplay of countless atmospheric variables. The position of high-altitude jet streams, the formation of low-pressure systems over the bay, and even distant weather patterns can cause the entire monsoon machine to temporarily sputter and stall. And this is what makes the monsoon so much more than just a season. It's a dynamic living system, a narrative that unfolds over 4 months. It has a beginning, the onset, a middle with active and break spells, and an end, the withdrawal. It has character, mood, and an almost biological rhythm. It is nature's delivery system for life, but the delivery is never guaranteed. The package can be delayed, damaged, or sent to the wrong address entirely. It is this inherent drama, this tension between its vital importance and its maddening unpredictability, that makes the monsoon the single most important and endlessly fascinating story on the Indian subcontinent. The machine is grand, but its gears are prone to slipping. You would think, in this age of technological marvels, that predicting the monsoon would be a solved puzzle. We have satellites that can see a single cloud from space. We have supercomputers that can perform trillions of calculations per second. We have a solid understanding of the fundamental physics. The land heats up, the ocean sends its moisture inland. It seems straightforward enough. And yet, year after year, the monsoon manages to surprise, confound, and humble us. The forecasts, crafted with immense data and expertise, can still be spectacularly wrong. This isn't a failure of science. It's a testament to the sheer mind-boggling complexity of the system we are trying to predict. It is a system born of chaos. Think back to 2015. The official forecasts confidently predicted a normal monsoon season. Farmers prepared their fields, governments planned their water allocations, and the nation collectively breathed a sigh of relief. But the rains never truly arrived with the force that was expected. Instead, India was gripped by one of the most severe droughts in decades, leading to widespread agricultural distress and water crises. The models had missed something. Some crucial piece of the puzzle had been overlooked or misunderstood. The system had behaved in a way that our best tools simply could not anticipate. This is the recurring nightmare for every meteorologist tasked with forecasting India's lifeline. The gap between prediction and reality can be a chasm. Why is it so difficult? Because predicting the monsoon is not like solving a simple equation. It's like trying to solve a Rubik's Cube where the colors of the squares are constantly shifting and changing on their own. It's a puzzle with countless moving parts, and each part influences all the others. The strength of the monsoon isn't determined solely by the temperature difference between the land and the sea. It is a product of a vast, interconnected network of atmospheric and oceanic phenomena, many of which are happening thousands of kilometers away from India. The perfect monsoon requires a perfect alignment of all these disparate factors, a delicate celestial symphony where every instrument must play in tune. This is the very definition of a chaotic system. In mathematics, chaos doesn't mean random. It means that tiny, almost immeasurable changes in the initial conditions can lead to wildly different and unpredictable outcomes. A butterfly flapping its wings in Brazil can, in theory, set off a tornado in Texas. For the Indian monsoon, there are dozens of such butterflies. A slight 1-degree variation in the sea surface temperature in the central Pacific, a pocket of unusually cold air high above Siberia, or a subtle shift in the high-altitude winds known as the subtropical jet stream. Any one of these can be the trigger that turns a normal monsoon forecast into a real-world disaster. Let's pull back the curtain and look at some of these chaotic variables, the ghosts in the monsoon machine that haunt forecasters. One of the most critical factors is the state of the Tibetan Plateau. This vast, elevated landmass, often called the roof of the world, acts as a gigantic radiator in the sky. During the summer, it heats up intensely, strengthening the low-pressure system over Asia and acting as a powerful engine that drives the monsoon circulation. But the amount of heat it radiates depends heavily on how much snow and ice cover it received during the preceding winter. A heavier than usual snowpack means more of the sun's energy is reflected back into space, keeping the plateau cooler and potentially weakening the entire monsoon flow. Then there are the winds. We are not talking about the surface winds you feel on your face. We are talking about the jet streams, fast-flowing, narrow rivers of air high up in the atmosphere, miles above the Earth. The subtropical westerly jet stream, which flows over northern India during the winter, must shift its position northward, moving to the north of the Himalayas, for the monsoon to set in properly. If this shift is delayed, it can act as a lid on the atmosphere, preventing the moist monsoon winds from rising and forming rain clouds. Predicting the precise timing of this large-scale atmospheric reorganization is one of the toughest challenges in meteorology, a crucial domino that must fall at the right moment. The chaos doesn't stop at the borders of Asia. We have to look even further afield, to places you would never think to connect with India's rains. Consider the dust storms that rage across the Sahara Desert and the Arabian Peninsula. For a long time, these were seen as entirely separate weather events. But we now know that these massive plumes of airborne dust and sand can travel across the Arabian Sea. These tiny particles, known as aerosols, can have a profound impact. They can alter the way sunlight is absorbed and reflected, and they can serve as nuclei around which water vapor condenses, potentially influencing the formation, size, and intensity of raindrops within the monsoon clouds. A dust storm in Africa can literally seed the clouds in India. And what about the oceans? The Indian Ocean is the immediate source of moisture, but its temperature is not uniform. Pockets of warmer or cooler water can form, influencing the evaporation rates and the stability of the air above. But the real wild card is the Pacific Ocean, an ocean away. A minor temperature shift in the equatorial Pacific, a phenomenon known as El Niño, can trigger a chain reaction that disrupts weather patterns globally. It can weaken the trade winds, alter pressure systems, and has been shown to have a strong correlation with suppressed rainfall and drought conditions in India. The monsoon, it turns out, is listening to whispers from oceans half a world away. The intricate web of connections means that the Indian monsoon is incredibly sensitive to global events. It is a system that feels the ripples from disturbances across the entire planet. A cyclone forming off the coast of Madagascar in the southern Indian Ocean might seem irrelevant to a farmer in Uttar Pradesh, but that cyclone can alter the large-scale pressure patterns and wind flows across the equator, subtly changing the path and intensity of the monsoon winds that will arrive in India weeks later. This is the challenge of modern forecasting. It's not enough to look at India's backyard. You have to monitor the entire globe for clues. Every weather system is connected in a delicate planetary dance. This interconnectedness makes long-range forecasting, the kind of prediction that tells us in April what the whole season from June to September will look like, an act of extreme scientific bravery. The forecasters are trying to predict the outcome of a chaotic system months in advance. They must account for the state of the Pacific Ocean El Niño, or La Niña, the temperature gradients in the Indian Ocean, which is called the Indian Ocean Dipole, the snow cover over Eurasia, the stratospheric winds, and honestly, a dozen other parameters. If even one of these factors behaves unexpectedly, the entire forecast can be thrown off course. It is a high-stakes game of probability, where the model must weigh all these dancing ghosts correctly. This sensitivity is why we see such dramatic year-to-year variability. One year, the conditions align perfectly. The Pacific is neutral, the Tibetan Plateau is hot, the jet stream moves on schedule, and India receives a bountiful, well-distributed monsoon. The next year, an El Niño develops, the plateau remains cool, and the result is widespread drought. This isn't the system failing, it's the system responding perfectly to a different set of global inputs. The monsoon is not a rogue element, it is a faithful messenger, delivering a verdict on the state of the entire planetary climate system. Its message, however, can be one of life or one of struggle. Ultimately, the chaos in the clouds reflects a profound truth about our planet. Everything is connected. The rain that falls on a field in Punjab is the end result of a story that began with sunlight in the tropics, snow in the Himalayas, and ocean currents swirling thousands of miles away. It is a system so complex, so interwoven, that it defies simple explanation and easy prediction. While our understanding grows with each passing season, the monsoon retains its power to surprise. It remains a wild, untamable force of nature, a beautiful and terrifying expression of the planet's chaotic elegance, reminding us that there are still deep mysteries left to solve in the sky above. Faced with a force as vital and volatile as the monsoon, the drive to predict its behavior is not a new one. The first systematic attempts to demystify the rains began not in a modern data center, but in the colonial offices of the British Raj. In the late 19th century, after a series of devastating famines linked to monsoon failures, the British administration realized that understanding this weather system was a matter of imperial stability. The task fell to scientists like Sir Gilbert Walker, the Director General of Observatories in India. He was a mathematician, not a meteorologist, and he approached the problem with a statistician's eye, believing that the monsoon's secrets were hidden not in the physics of the clouds, but in the cold, hard data of the past. Sir Gilbert and his team embarked on a colossal data-gathering mission, collecting decades of weather records from across the globe. They were searching for patterns, for statistical correlations that could serve as predictive clues. They noticed strange, long-distance connections, what they termed teleconnections. For instance, they observed a peculiar inverse relationship. When the atmospheric pressure was high in the South Pacific, it tended to be low in the Indian Ocean, and vice versa. This oscillation, which Walker named the Southern Oscillation, was found to have a direct link to the strength of the monsoon rains in India. It was a groundbreaking discovery, the first time anyone had scientifically linked India's weather to conditions halfway around the world. This pioneering work laid the foundation for India's first weapon in the forecasting war, the statistical model. The India Meteorological Department, or IMD, developed and refined this approach over the next century. The model was built upon a set of carefully selected predictors, known as the 16 parameters. These were a mysterious and eclectic mix of atmospheric and oceanic variables measured in the months leading up to the monsoon season. They included things like the sea surface temperatures in the Pacific, the air pressure over Mauritius and Darwin, the snow cover over the Himalayas, and even the air temperature over northern Europe. It was a recipe for prediction, a statistical soup of global climate signals. Every year, in April, the values for these 16 parameters would be collected and fed into a complex regression equation. The resulting number would become the official long-range forecast for the entire country, a prediction of whether the seasonal rainfall would be above normal, or below normal. For decades, this statistical model was the backbone of Indian monsoon forecasting. It was relatively fast, computationally inexpensive, and it worked to a degree. It was like using a well-worn, dusty map to navigate a treacherous landscape. It provided a general sense of direction, but it couldn't see the sudden pitfalls or unexpected detours that lay just ahead on the journey. The statistical model was a remarkable achievement for its time, a testament to the power of finding patterns in historical data. However, its greatest strength was also its most profound weakness. It was fundamentally based on the past. The model assumed that the relationships observed between the 16 parameters and the monsoon over the last 50 or 100 years would continue to hold true in the future. It was, well, an exercise in looking in the rearview mirror to predict the road ahead. For a long time, this assumption held up reasonably well, as the global climate system remained relatively stable. But as the 20th century progressed, this method began to show its age, and its limitations became dangerously apparent. The primary issue was that the model was blind to sudden, dramatic shifts in the climate system. It could not see a surprise coming. The most significant of these surprises was El Niño. While Sir Gilbert Walker had discovered its atmospheric component, the Southern Oscillation, the full dynamics of the coupled ocean-atmosphere phenomenon were not well understood for many more decades. A strong El Niño event could develop rapidly in the Pacific Ocean between April, when the forecast was made, and July, the peak of the monsoon season. The statistical model, based on pre-season data, would be completely oblivious to this massive disruption brewing in the Pacific, a disruption that almost invariably leads to a weaker monsoon and potential drought in India. Furthermore, the statistical relationships themselves were not static. They could weaken or even reverse over time. This is known as epochal variability. A parameter that was a reliable predictor for 30 years might suddenly lose its predictive power for the next 30. Scientists found that the correlation between Himalayan snow cover and monsoon rainfall, once a cornerstone of the model, had significantly weakened in recent decades. The climate system was evolving, but the statistical model was stuck in the past, relying on relationships that were no longer as robust as they once were. It was like navigating with a map that was slowly becoming obsolete as the landscape itself changed. This meant the model was particularly bad at forecasting the extremes, the very events that caused the most damage. It was reasonably good at predicting normal years, because normal is, by definition, the most common outcome. But it consistently failed to predict the major droughts of 2002, 2004, and 2009. It was a system designed for averages, not for outliers. In a world facing increasing climate volatility, relying solely on historical statistics was becoming a high-stakes gamble. India needed a new tool, one that did not just look at the past, but could simulate the future. It needed to move from stats to physics, from correlations to supercomputers. The turning point came with the severe monsoon failures of the early 2000s, which exposed the vulnerabilities of the old statistical model for all to see. The scientific community and the Indian government recognized that a paradigm shift was necessary. The world of meteorology was moving towards a new frontier dynamical modeling. This approach does not rely on historical correlations. Instead, it attempts to simulate the entire Earth's climate system from the ground up, using the fundamental equations of physics, fluid dynamics, and thermodynamics that govern the behavior of the atmosphere and oceans. It was a monumental leap in complexity and ambition, and it required one thing above all else: massive computational power. In 2012, India officially launched the National Monsoon Mission, a hugely ambitious and well-funded project with a clear goal: to build and implement a state-of-the-art dynamical modeling system for monsoon prediction. The mission brought together the country's brightest minds from institutions like the Indian Institute of Tropical Meteorology in Pune and the National Centre for Medium-Range Weather Forecasting. The aim was to develop a seamless prediction system that could provide forecasts across different timescales, from short-range weather, a few days, to extended range, a few weeks, and most critically, the long-range seasonal forecast for the monsoon itself. Inside centers like IITM, young scientists began working with a powerful new tool, a coupled climate model. This is not just a computer program, it is a virtual Earth. It is a three-dimensional grid that blankets the entire globe, extending from the bottom of the ocean to the top of the atmosphere. Each cell in this grid contains the mathematical equations that describe the physics of the climate. The model simulates the movement of every wind current, the formation of every cloud, the swirling of every ocean gyre, and the transfer of heat and moisture between them. It is an attempt to create a digital twin of our planet's climate engine in real time. This new approach represented a fundamental change in philosophy. Instead of asking, what happened in the past when conditions were similar, the dynamical model asks, given the current state of the atmosphere and oceans right now, what will the laws of physics do next? It does not just look at history, it attempts to run a simulation of the future. This is an infinitely more powerful technique. It can, in theory, capture the sudden onset of an El Niño or other unexpected events, because their development is governed by the same physical principles that are coded into the model. The era of the supercomputer had arrived, promising to finally tame the chaos of the monsoon. The implementation of these dynamical models was a game-changer. For the first time, forecasters could watch a virtual monsoon unfold on their computer screens months before the real one was due to arrive. The process begins by feeding the supercomputer an enormous amount of real-time data to establish the initial conditions. This includes millions of observations from satellites, weather balloons, ocean buoys, and ground stations all over the world. This data provides a comprehensive snapshot of the Earth's climate system at a specific moment in time. Once this initial state is set, the supercomputer is switched on, and it begins to solve the millions of physics equations to calculate how the system will evolve over the next few hours, days, and months. However, because the monsoon is a chaotic system, even the tiniest error in the initial data can lead to a wildly different forecast down the line. To account for this uncertainty, scientists do not just run one simulation, they run an ensemble. They run the model dozens of times, and for each run, they make a tiny, physically plausible tweak to the initial conditions. This creates a whole family of possible futures. If most of the simulations in the ensemble predict a strong monsoon, forecasters can have high confidence in that outcome. If the simulations show a wide spread of possibilities, from drought to flood, it signals that the forecast is highly uncertain. This new capability has led to significant improvements in forecasting accuracy. The dynamical models are far better at predicting the onset of the monsoon over Kerala and its progression across the country. They are also much more skilled at capturing the influence of large-scale climate phenomena like El Niño and the Indian Ocean dipole, as these are emergent properties of the physics being simulated. The models can now provide more detailed spatial forecasts, predicting which regions of the country are likely to receive more or less rain, something the old statistical model, which only gave a single number for the whole country, could never do. But even with petabytes of data and the fastest supercomputers on the planet, the system is still not perfect. It still struggles to tame the inherent chaos of the clouds. In one notable year, the model predicted lower than average rainfall, but a series of unexpected low-pressure systems in the Bay of Bengal led to a late-season surge that ended up flooding states like Bihar. The models are still grappling with accurately simulating the precise formation of clouds and the complex interactions with Himalayan terrain. The supercomputers gave us a powerful new lens to look at the future, but they also revealed just how deep the complexities of the monsoon truly are. The battle between prediction and chaos was far from over. Just as supercomputers revolutionized forecasting by replacing statistics with physics, a new and even more disruptive force is now entering the arena. The next great leap in our quest to predict the monsoon is not coming from better physics alone, but from a completely different way of thinking about data. Meet the new forecaster on the block: artificial intelligence. AI and machine learning models represent a paradigm shift, moving beyond human-devised equations and into the realm of self-learning algorithms. These systems are designed to ingest colossal amounts of data, far more than any human or even a traditional model could handle, and teach themselves to find the hidden patterns within that data. Patterns that we may not even know exist. The game is changing once again. Imagine an ambitious student at IIT Delhi, not with a weather chart, but with a deep learning algorithm. They feed the system every conceivable climate variable from the past century: sea surface temperatures, atmospheric pressure grids, wind speeds at multiple altitudes, soil moisture levels, aerosol concentrations, and millions of other data points. The AI is not given any pre-existing theories about how the monsoon works. It is simply told, here is the data for the last 100 years, and here is the rainfall that actually occurred. Find the connections. The machine then churns through this mountain of information, building its own intricate, non-linear model of the monsoon system, free from the constraints of human intuition and established meteorological theory. This approach is incredibly powerful because AI excels at dealing with the very chaos that plagues other models. Where a physicist sees noise in the data, a machine learning algorithm might see a faint but significant signal. It can identify complex, multidimensional relationships that are impossible to represent with a clean mathematical equation. For example, an AI might discover a unique combination of specific ocean temperature anomalies in the South Atlantic and a particular wind pattern over Siberia that, when occurring together, have an 85% probability of leading to a delayed monsoon onset over northeast India. This is a level of nuanced pattern recognition that goes far beyond what previous methods could achieve. Major technology giants and innovative startups are now racing to apply this power to climate science. Google's Earth Engine provides a planetary-scale platform for geospatial data analysis, allowing researchers to train AI models on decades of satellite imagery. IBM's GraphCast, a revolutionary AI weather model, has already shown astonishing results in predicting global weather patterns with greater accuracy and speed than traditional systems. Indian startups are also entering the fray, developing bespoke AI tools tailored specifically to the subcontinent's unique climate challenges. The age of AI is not just about smarter phones, it's about a smarter, more insightful, and potentially more accurate way of forecasting the fate of a billion people. The true beast mode of artificial intelligence lies in its ability to find meaningful patterns in what appears to be pure madness. Traditional models are built on our understanding of physical laws, which works well for large-scale, well-understood phenomena. But the monsoon is full of smaller, localized and chaotic processes like the exact formation of a thunderstorm or the development of a low-pressure system that are incredibly difficult to simulate with physics alone. AI takes a different route. It doesn't need to understand the physics perfectly. It just needs to recognize the statistical fingerprint that precedes a particular outcome. It learns from observation, much like a seasoned sailor who knows what a certain type of cloud on the horizon means, but on a superhuman scale. This has already led to some stunning breakthroughs. In early 2024, a flash flood devastated parts of Sikkim. Traditional satellite-based warnings and weather models gave only a limited heads-up. However, an experimental AI system, which had been trained on a massive dataset of regional weather patterns and river flow data, had flagged a high probability of a catastrophic event 3 full days earlier. It had detected a subtle combination of atmospheric moisture, temperature gradients, and unusual snowmelt rates that, to a conventional model, might have seemed insignificant. But the AI had learned from past events that this specific combination was a recipe for disaster. It saw the pattern in the madness. This capability is particularly vital for predicting extreme weather events, which are becoming more frequent in a warming world. While dynamical models are good at forecasting the average rainfall over a season, they often struggle with the sudden, intense downpours that cause the most damage. AI models, trained specifically on data from past extreme events, are proving to be much more adept at this. They can learn the unique atmospheric signatures that precede a cloudburst over the Himalayas, or a cripplingly intense rainfall event over a coastal city. This is the holy grail of short-range forecasting, not just predicting rain, but predicting its destructive potential. The ultimate goal is to create a hybrid system, a centaur model that combines the strengths of both approaches. This system would use the powerful physics-based dynamical models to simulate the large-scale atmospheric flow, providing a robust foundation for the forecast. Then, an AI layer would be applied on top of this simulation. The AI would act as a sophisticated post-processor, scanning the model's output for subtle patterns of error it has learned to recognize, and correcting the forecast for localized and extreme events that the physics model might miss. It's the fusion of human knowledge, represented by the laws of physics, with the inscrutable, pattern-finding genius of the machine, a potent combination in the ongoing battle to decode the monsoon. No matter how advanced our supercomputers or how intelligent our AI, all forecasting will ultimately fail if we do not respect the immense power of the world's oceans. The atmosphere may be where the weather happens, but the ocean is where it is born. The oceans are the planet's memory, storing vast amounts of heat and releasing it slowly over months and years, setting the background conditions that dictate the fate of weather systems everywhere. The Indian monsoon is particularly sensitive to these oceanic mood swings. There are several secret switches hidden in the depths of the global oceans, and flipping any one of them can completely rewrite the monsoon's script for the year. The most famous of these switches is the El Niño Southern Oscillation, or ENSO, located thousands of miles away in the tropical Pacific Ocean. In a normal year, trade winds push warm surface water towards Asia. But during an El Niño event, these winds weaken or even reverse. A massive pool of warm water builds up in the eastern and central Pacific. This seemingly distant event triggers a massive atmospheric chain reaction. It alters the Walker circulation, a key component of global atmospheric flow, which in turn weakens the low-pressure system over India and suppresses the monsoon rains. As a fisherman in Tamil Nadu might observe, when the distant water turns warm, the rains come late and weak. His ancient wisdom reflects a profound scientific truth. The opposite of El Niño is La Niña, when the Pacific waters become unusually cold. This condition typically has the reverse effect, supercharging the monsoon and often leading to above-average rainfall and major floods across India. But the Pacific doesn't hold all the cards. The Indian Ocean has its own climatic heartbeat, a phenomenon known as the Indian Ocean Dipole, or IOD. This is a sort of east-west seesaw of sea surface temperatures. In a positive IOD event, the western Indian Ocean becomes warmer than average, while the eastern part cools. This temperature gradient boosts the monsoon, often bringing good rains to India even if a weak El Niño is present. A negative IOD does the opposite, acting as another brake on the monsoon. The web of influence extends even further, into the vast expanse of the Atlantic Ocean. The Atlantic Multi-Decadal Oscillation, or AMO, describes long-term, slow-moving changes in sea surface temperatures there. A warm phase in the Atlantic has been linked to more active monsoon seasons in India decades later. And as we've seen, even a cyclone forming off the coast of Madagascar can send atmospheric ripples northward, influencing rainfall in Mumbai 2 weeks later. The message is clear. The Indian monsoon is not a local affair. It is a global phenomenon, a system intricately wired into the health and rhythm of the entire planetary ocean system. To forecast the rain in India, you must first listen to the whispers of the deep. Nowhere is the dramatic, chaotic, and life-altering power of the monsoon more visible than in the sprawling metropolis of Mumbai. Every year, from June to September, this city of over 20 million people braces for an annual battle with the sky. The monsoon is Mumbai's lifeline, replenishing the lakes that provide its drinking water. But it is also its recurring tormentor, a force that regularly brings the maximum city to its knees. The story of the Mumbai monsoon is a visceral, real-world case study in the limits of prediction and the raw power of wild weather. It is a place where all the complex theories of meteorology crash into the hard reality of urban life. The defining moment in the city's modern monsoon history is etched into its collective memory. July 26, 2005. On that single terrifying day, the heavens opened up and dumped an unprecedented 944 millimeters, over 3 feet, of rain on the city. It was a deluge of biblical proportions. The city's infrastructure, already straining, collapsed completely. The suburban train network, Mumbai's circulatory system, stopped dead. Roads vanished beneath murky, swirling floodwaters, transforming into canals of debris. Cars and buses were submerged, and thousands of people were stranded for hours, forced to wade home through chest-deep water. The city was paralyzed, cut off from the world, a stark reminder of its vulnerability. This event was a brutal lesson. It wasn't just the amount of rain, but the intensity. The city received the bulk of that rainfall in just a few terrifying hours, overwhelming a drainage system that was centuries old and designed for a much gentler climate. Ever since, every monsoon season in Mumbai is accompanied by a sense of dread and a ritual of preparation and anxiety. Citizens track weather apps with nervous intensity. The media runs constant updates on high tides, which can prevent rainwater from draining into the sea, exacerbating flooding. Viral videos of floating auto rickshaws, waterlogged train stations, and daring rescues become an annual social media tradition. Despite being India's financial capital, a hub of technology and innovation, the city still struggles with one fundamental mystery: predicting with precision exactly when and where the most intense spells of rain will hit. Forecasters can issue a red alert for extremely heavy rainfall for the entire metropolitan region, but can they tell you that the Bandra Kurla complex will get 200 millimeters of rain between 2 p.m. and 4 p.m., while Colaba, just a few kilometers south, will get only 50 millimeters? Not yet. This hyperlocal, short-term prediction is the final frontier. For Mumbaikars, the difference between a normal rainy day and a city-stopping deluge can be just a few hours of intensely localized weather, a wildness that continues to elude our grasp. So after this journey through statistics, supercomputers, and artificial intelligence, we have to ask the ultimate question. Can we actually trust the forecast? Let's be brutally honest. The answer is a complex and sometimes frustrating yes. But while our ability to predict the monsoon has improved dramatically over the last 2 decades, the system remains a master of deception, particularly when it comes to its most violent and unpredictable moods. We have become very good at predicting the big picture, the seasonal average. But the monsoon story is often written not in the averages, but in the devastating extremes. And this is where our vision still gets blurry. The science has advanced, but the chaos has not been fully tamed. Consider the events of 2019. In its official long-range forecast, the India Meteorological Department predicted a near-normal monsoon season. This forecast, generated by sophisticated dynamical models, suggested a season of adequate and well-distributed rains. For the first month, this seemed to hold true. But then, starting in July, the character of the monsoon shifted violently. A series of powerful, slow-moving weather systems began to form, unleashing relentless, record-breaking rainfall across the country's western and central states. By August, the near-normal forecast had become a distant memory, as 15 different Indian states were grappling with some of the worst floods they had seen in years. This is the core of the problem. A seasonal forecast that correctly predicts the countrywide average rainfall, say 102% of the long-term average, can be technically accurate, but practically useless if that rain arrives in a few catastrophic bursts rather than a steady, gentle flow. One part of the country could experience a drought for 2 months, only for the seasonal average to be corrected by a single week of biblical floods. The models are getting better at predicting the total quantity of water that will be delivered, but they still struggle immensely with predicting the timing, distribution, and most importantly, the intensity of that delivery. For a farmer, a week of floods followed by a month of no rain is far worse than a season of slightly below average but consistent rainfall. This highlights the immense challenge that remains. We can forecast the general trend of the monsoon with a fair degree of confidence. We know if an El Niño is likely to suppress the rains, or if a positive Indian Ocean dipole might give them a boost. This is invaluable information for national-level planning, for managing water levels in massive reservoirs, and for strategic food grain policy. But for the citizen on the ground, for the farmer waiting to sow their seeds, or for the city dweller worried about their street flooding, this broad strokes forecast is not enough. The trust in the forecast is therefore conditional, a trust in the general direction, but a deep-seated skepticism about its ability to predict the sudden, life-altering storms. When we zoom in from the national seasonal forecast to the local daily reality, the picture of trust and utility changes completely. While the long-range forecast might miss the mark, the improvements in short-range weather prediction have been nothing short of revolutionary. On the ground, most critical decisions are not based on seasonal forecasts, but on highly detailed, location-specific 5-day and even 3-day forecasts. These short-term predictions are the real workhorses saving lives and livelihoods every single day across the subcontinent. For an Indian farmer, this has been a game-changer. In the past, deciding when to sow seeds was a gamble based on tradition, instinct, and hope. Sow too early, and seeds might wither in a dry spell. Sow too late, and you miss the growing season. Today, that same farmer can receive a reliable 5-day forecast for their specific district via text message or mobile app. This allows for tactical, informed decisions to sow seeds now, to delay planting, to apply fertilizer before rain, or to harvest before a hailstorm. This last-mile delivery is where trust is being built, day by day. State governments now heavily rely on district-level forecasts to issue agricultural advisories. Disaster management teams pre-position resources and issue evacuation warnings ahead of flash floods or cyclonic storms. Urban administrators in Mumbai or Chennai use short-term rainfall predictions to manage drainage systems and alert citizens about waterlogging in specific zones. The forecast is no longer abstract for the whole country. It has become a concrete, actionable tool for daily life. However, even at this local level, the future remains foggy beyond a 5 to 7 day window. The holy grail for meteorologists and for every Indian citizen is the extended range forecast, a reliable prediction for 2 to 4 weeks. Imagine telling a farmer in mid-July that a 2-week monsoon break is coming. This would allow water-saving measures and preparation for the dry spell. While some progress is being made, these medium-range forecasts are still considered experimental and have low confidence. The ground truth is short-term trust is high, but long-term certainty remains elusive. So, while the present state of forecasting is a mix of impressive success and frustrating limitations, the future looks incredibly bright. The quest to perfectly predict the monsoon is driving a wave of innovation that promises to give us a much sharper, clearer vision of the chaos in the clouds. The next generation of tools is already on the horizon, moving us closer to a world where monsoon forecasting is not just more accurate, but more personal, more immediate, and more useful to every single individual. The foggy future is, bit by bit, coming into focus, and the technology leading the charge is truly awe-inspiring. India's space agency, ISRO, is at the forefront of this revolution. Upcoming satellite missions are being designed specifically with the monsoon in mind. These new eyes in the sky will not just take pictures of clouds, they will be equipped with advanced microwave sounders and cloud-penetrating radar that can measure rainfall rates, cloud moisture content, and atmospheric temperature profiles with unprecedented detail and frequency. Instead of getting updates every few hours, we could soon have a near real-time, three-dimensional view of the entire monsoon system as it evolves, feeding a constant stream of high-quality data into our weather models. This fire hose of new data will be the perfect fuel for the next generation of AI and machine learning models. As AI systems become more powerful, they will be able to auto-update and self-correct forecasts in real time as new satellite data pours in. Imagine a national forecast that is no longer static, but is a living document, constantly refining its predictions for every district, every city block, every single hour. This is the dream of nowcasting, the ability to predict weather in the immediate future with pinpoint accuracy. The ultimate goal is to one day provide a farmer in a remote village in Odisha with a personalized voice alert in their local language. Heavy rain expected in your village in the next 48 hours. Please delay planting. And looking even further ahead, the nascent field of quantum computing holds the potential to blow the doors off our current capabilities. The sheer complexity of simulating the Earth's entire climate system is a task that pushes even the biggest supercomputers to their limits. A fully realized quantum computer could, in theory, perform these impossibly complex simulations in a matter of minutes, not weeks. It could run millions of ensemble forecasts simultaneously, exploring every possible future and giving us a true probabilistic map of the monsoon's intent. We may one day be able to generate a reliable village-level monsoon forecast a month or more in advance. The journey to trust the forecast is a long one, but we are getting closer with every season. We have journeyed from the fundamental physics of a planetary heat engine to the wild, untamable chaos in the clouds. We have traced the evolution of our predictive tools from the simple statistical correlations of the British Raj to the mind-bending complexity of today's AI and supercomputer models. We have seen how the monsoon is not a singular event, but a two-armed giant, a system of breathtaking scale whose fate is intertwined with the whispers of distant oceans and the dust from faraway continents. It is a system that gives life with one hand and takes it away with the other. A force that defines the very rhythm of existence for more than 1 billion souls on the Indian subcontinent. The central question we began with, can we really predict the monsoon, does not have a simple yes or no answer. Instead, what we have discovered is a deeper appreciation for the sheer magnificence of the challenge. The story of monsoon forecasting is a thrilling narrative of human ingenuity, relentlessly pushing against the boundaries of the unknown. Every failed forecast, every surprise flood, every unexpected drought has not been a defeat, but a lesson. It has been a clue that has forced scientists to look deeper, to expand their models, and to forge new tools to peer into the heart of the storm. The quest to predict the monsoon is, in itself, a testament to our species' unyielding curiosity. The progress we have made is undeniable. The move from simple statistics to dynamical physics, and now to the pattern-finding genius of artificial intelligence, represents a quantum leap in our understanding. We can now anticipate the influence of global phenomena like El Niño with a confidence that was unthinkable just a few decades ago. Our short-range forecasts provide actionable, life-saving information to farmers, city planners, and disaster management teams on a daily basis. The future promises even more, with next-generation satellites and quantum computing holding the potential to give us a vision of the weather that is sharper and more personal than ever before. Yet for all our technological prowess, the monsoon retains its essential wildness. It remains a system born of chaos, a serenade where order and unpredictability are locked in an eternal dance. We may build better models, gather more data, and design faster computers, but the inherent nature of a chaotic system is that it will always hold the power to surprise us. The goal may not be to achieve perfect prediction, for that may be impossible. Rather, the goal is to continuously narrow the cone of uncertainty, to replace fear with preparedness, and to learn to listen more closely to the intricate, powerful song of the clouds. In the end, the story of the monsoon is much more than a tale of meteorology. It is a story about India itself. It is a reflection of the nation's resilience in the face of uncertainty, its deep connection to the cycles of nature, and its constant striving for progress against immense challenges. The annual arrival of the rains is a cultural touchstone, a source of poetic inspiration, and the engine of the economy. The shared experience of waiting for the monsoon, of celebrating its arrival, and of enduring its fury is a thread that binds together a diverse population of over 1 billion people. The monsoon is woven into the very fabric of Indian identity. We may never fully tame this magnificent beast. We may never solve its deepest mysteries to the point where all surprise is eliminated. And perhaps in some way, that is for the best. The monsoon's enduring unpredictability serves as a powerful and humbling reminder of our place within the natural world. It teaches us that despite our technological advancements, we are still subject to forces far greater than ourselves. It demands respect, it encourages adaptation, and it forces us to innovate. The continuing challenge of the monsoon ensures that we never stop learning, never stop questioning, and never stop looking up at the sky with a sense of wonder. The journey to understand this phenomenon is a marathon, not a sprint. With every passing season, with every new satellite launched, with every algorithm refined, we get a little bit closer. We learn from the floods of one year and the droughts of the next. The knowledge we gain is not just academic. It is paid for in the hard-won experience of the farmers, fishermen, and city dwellers who live by the monsoon's whims. Their ancestral knowledge, combined with the cutting-edge science of our time, creates a richer, more complete picture of this vital, life-giving system. The monsoon is life. It floods us, it feeds us, and it ultimately defines who we are. We may never completely conquer its chaos, but our relentless quest to understand its song is one of the great scientific and human adventures of our time. With every drop of rain that falls, we add another note to our understanding, getting ever closer to deciphering the beautiful, complex, and enduring secrets of India's weather. The mystery continues, and so does our journey into the heart of the storm, rain, or shine.